So noise temperature, noise bandwidth. So continuation of last video. So noise temperature, noise bandwidth. How we can calculate noise temperature and noise bandwidth? So using Johnson-Nyquist noise equation, we can calculate noise temperature and noise bandwidth. So we say that power spectral density of noise expressed the term, the equation. The equation is shown Pn divided by B equal to Kb divided by Kb into T. So what is P? Is a noise power, and B is a total bandwidth, and Kb is a Boltzmann constant, and T is noise temperature. So Pn is a noise power, the unit is watt, and B the total bandwidth which is noise is measured, and Kb Boltzmann constant 1.381 into 10 to the power of 23 joules per Kelvin, and T noise temperature. So based on this equation, we have to find it what is noise temperature and noise bandwidth. Yeah, T is a temperature, that is equal to, we have to rearrange that equation, then P divided by B dot 1 by Kb. We know what is P, it's a noise power, B is bandwidth, and Kb is a Boltzmann constant. What is the Boltzmann constant value? 1 point, what is value? 1.381 into 10 to the power of minus 23 joules per Kelvin. So we found the temperature. Similarly, we can easily found the bandwidth also based on the equation. If we rearrange the equation, we will get the bandwidth value also. What about wireless communication receiver temperature? That means noise temperature. What is wireless communication? So there is a transmitter and receiver. Between there is no wire. It's a free space. Then we can call as a wireless communication. If it is a wireless communication receiver, so what's the equivalent temperature of that wireless communication receiver? So you have to sum up of two temperature. That temperature is nothing but the receiver having, you just split the receiver into two parts. The one is antenna, another one is system or components. So what's the use of antenna? Antenna will receive the signal from transmitter and sending to the output sent to the receiver. So that antenna is the first primary component of the receiver. That receiver has a total equivalent temperature. That temperature also it's a noise temperature of the antenna plus system temperature. It is nothing but the receiver has a component. That component we can call as a system. So system temperature antenna. So these two temperature noise will be sum up or add, then you will be getting the final output, that's the equivalent temperature of the wireless communication receiver. We understand? Okay. So next, noise temperature of the cascade devices. The noise temperature of the cascade devices is commonly measured using Y factor method. How you say it is nice temperature? Yeah, you know, it is not a just one device. There's so many devices. So multiple devices are present and they in cascade manner. That is called as noise temperature in cascade manner. So if you want to calculate noise power in one device, you will be go to the internal equations. Like just now we saw the equation for found the noise temperature of wireless communication system. Similarly, we can calculate using that equation. But it is not just one device; it is more than one. If it is more than one, even it is not just a place; it is placed as a cascade manner. Then how can calculate the noise power of the equation? So using this Fry's equation, we can calculate the noise temperature of cascade equations. So T equivalent T1 plus T2 divided by G1 plus T3 divided by G1 G2. So these equations representing multiple amplifier in cascade manner, we can find the temperature noise temperature of that system, total system. So what is T1, what is G1? T1 is a noise temperature, and T2, what's the noise temperature of T1? First component. Similarly, T2 is the second component of the noise temperature, and T3 is the third component of the noise temperature. And G1 is a gain power of first component, and G2 gain power of second component. So T equivalent T1 plus T2 G1 T3 plus G1 G2, okay, anything okay. For if you consider might be there are four amplifier present in cascade manner, how the equation might be present, can you assume? Yeah, T equivalent equal to started T1 plus T2 G1 plus T3 G1 G2, then T4. Why it is T4? Because there it is four components. If it is presented 5, T5. So T4 divided by G1, G2, G3. So this is the equation for while four amplifier present in cascade manner. We can write the equation like that. If it is 6 or 7 components, might be if it is considered as 6, start at T1, then ended with T6, and G1 ended with G5. Okay, so this is noise temperature of cascade devices. Okay, thank you.